Implicit differentiation. Let's start by defining an explicit function. An explicit function is a function in which the dependent variable can be written explicitly in terms of the independent variable. So for example, we're used to seeing explicit functions of the form y equals f of x. So the variable y is the dependent variable because it depends on whatever is substituted into this value of x. So x is the independent variable. So we're used to seeing explicitly defined functions. So given y equals 3x squared minus 2x plus 1, we've been given an explicit function, so y is dependent upon whatever we substitute into the independent variable x. And we're used to finding derivatives of these functions in this form. So find y prime. So what I want to do is remember, though, that being asked to find y prime is equivalent to being asked to find dy dx. And another way of being asked to find dy dx is being asked to find the derivative with respect to x, so d dx of y, of the function y. So the reason why I want to remember this right now is because I actually want to solve this using a different set of steps than we normally do. So normally we would just jump straight to that the left side is y prime. So we would just go ahead and write y prime equals and then use the power rule on the right hand side. What I want to do instead is think about, instead of just jumping straight to y prime, what we're really doing is we're taking the derivative with respect to x of both sides of the equation. So d dx of what's on the left, the name of the function y, or that dependent variable, and then we're also taking the derivative with respect to x of the right side, 3x squared minus 2x plus 1. So now d dx of y is exactly dy dx. So dy dx is the left side, and the right side can be found applying the power rule. So 6x, right, bring the power to the front, and then reduce the power by 1. Then 2x just becomes 2, and then my constant 1 becomes 0. So now dy dx equals 6x minus 2. And again, dy dx was y prime. So y prime is 6x minus 2. So I just wanted to go through this seemingly straightforward problem, and it is, but just understanding the notation in a different way. So we're used to solving algebraic equations where whatever I do to one side, I have to do to the other. Technically, that's what we've been doing the whole time. We've been taking the derivative of y and then the derivative of the right-hand side. So now the derivative with respect to x of y is dy dx, and dy dx is y prime. And then on the right side, we apply the different rules and formulas that we have for finding the derivative when all of the variables are x. So now let's move on to looking at an implicitly defined function. Now, an implicit function or relation. A function or relation in which the dependent variable is not isolated on one side of the equation. So for example, if I have the equation x squared plus y squared equals 1, this represents an implicit relation. Specifically, this is a circle. So we tend to avoid using the term function because, as you can see, a circle does not pass the vertical line test, so a circle is not a function. So x squared plus y squared equals 1, this implicit relation, has it such that the dependent variable, the y, is not isolated on one side of the equation. And it often cannot be isolated on one side of the equation. So in other words, if I attempt to solve this for y, so if I get y squared by itself by subtracting x squared to the other side, in order to get y by itself, what's going to happen is I'm going to create two different equations, because when I take the square root of both sides, I'm going to get out plus or minus. So I now no longer have just one equation, I have two. I have y equals positive the square root of 1 minus x squared. So that's actually the top of the circle. And then I have y equals negative the square root of 1 minus x squared, and that's the bottom of the circle. So separately, each of those are functions. So the top of the circle just by itself would pass the vertical line test. And the bottom of the circle, just by itself without the top, would pass the vertical line test. And these are two separate functions. But the way we were given our equation to begin with, x squared plus y squared equals 1, this is an implicit relation. It defines two functions when solving for y. But if we want to find the derivative of this implicit relation, we're going to have to use implicit differentiation. So let's say we were given x squared plus y squared equals 1, and we're asked to find dy dx. So we're being asked to find the derivative of the function y with respect to x. What we're going to do is we're going to take the derivative with respect to x of both sides of the equation. So we're going to start all of our problems by taking d dx, so not dy dx, we're trying to find dy dx. We're going to take d dx, we're going to take the derivative with respect to the variable x of both sides. So d dx of x squared plus y squared, that's the left side, and then d dx of 1. Alright, so what we're going to do is we're going to take the derivative of the right side of the equation first, because that's fairly straightforward. The derivative of a constant is just 0. So the right side ends up being just a 0. And now we have to think about the left side. So let's remember we're taking the derivative with respect to the variable x. So the first term, x squared, is only in terms of the variable x, so we're going to use just our normal power rule for finding the derivative of x squared. So we have just 2x. But when we get to the derivative with respect to x of y squared, something different is going to happen. So what I'm going to do is I'm going to pull that problem off to the side. So the derivative with respect to x of y squared. So notice that the variables don't match. So we're doing something different. What we have to do is think about the fact that the variable y is a function of x. So remember that y equals f of x. So what I can do instead is think about this as the derivative with respect to x of f of x squared. So y is a function of x, so I'm choosing to write y as f of x. So now the derivative with respect to x of f of x squared, I can solve this using the chain rule. I have generic f of x inside the function x squared. So the derivative of f of x as a quantity squared, well, I bring the power to the front, and then I leave the inside function the same. And then I'd have to multiply by the derivative of the inside. So the derivative of f of x, all I can really do is write it as f prime of x. So now, to f of x, well, we said f of x was really just y. So this is like 2y times f prime of x. But what we're going to do is instead of f prime of x, we're going to write f prime of x as dy dx. So we're choosing to write f prime of x as dy dx because we were asked to find dy dx. So we are not going to use y prime, and you will see your textbook and other sources use y prime instead of dy dx, but here's exactly the reason why we're not going to do that. If I write 2y prime, a lot of people confuse y prime for y to the first, and then somehow this magically becomes 2y squared, which is definitely not the same thing. It's not the case, and that's what happens all the time, is mixing that up. That because y prime kind of does look like y to the first. So a lot of simplifying happens when no simplifying can happen. So we're not going to use this notation. We are going to use the dy dx notation for f prime of x. So here's what I want to focus on though. We're not going to do this every single time. Here's what I want you to notice, that I was taking the derivative with respect to x of y squared. And my final answer was 2y dy dx. Well, the reason why it's 2y is because it's just like we're taking the derivative as if this variable were an x. So if this was an x, it would just be 2x. Well, since it's a y, it's going to be 2y. But because the variables didn't match, we had an x and a y, I'm going to need the dy dx to follow through multiplication. So 2y times dy dx. So let's go back and substitute that in. So remember, I took the derivative of x squared, that was 2x. The derivative of y squared, so I'm going to have plus 2y. So just when the variables don't match, I take the derivative with respect to the variable x, meaning that in this case it's going to be 2y, but because it was with respect to the variable x, I have to include a dy dx. Alright, so now we have to do some additional work if we are to solve for dy dx. I need to isolate that piece. So I'm going to subtract the 2x to the other side. So 2y dy dx equals negative 2x if I subtract it over. And then I have to divide both sides by 2y. So the 2y's are going to cancel. Whoops, my page got off center. So my 2y's are going to cancel, and I end up with dy dx equals negative x over y. So let's notice something else, that in the past all of our derivatives have been only in terms of one variable. Now with implicit differentiation, I have both an x and a y in my derivative answer. So I have found dy dx, it is negative x over y. So now let's go ahead and try to make the connection on a graph. So remember we said that x squared plus y squared equals 1 was the equation of a circle and with radius 1. So remember, derivatives represent the slope of a tangent line. And now I want to think about why this particular derivative has both an x and a y in it. So let's say I was trying to find the slope of the tangent line at some value on this circle. So I want to know the slope of the tangent line right here. If I were to only go back and look at this particular x value, let's say it was 1/2. Let's just say this x value was 1/2. If I were to just substitute 1/2 into the x value, if this derivative was just in terms of x, how do I know that I'm finding the slope of the tangent line at this point or the one down here at this point? So both of these coordinate points have x values 1/2. So this is 1/2 something, some negative something, and this is 1/2 some positive something. So I need to know the y coordinate in order to find this particular slope of the tangent line, because this slope is obviously negative and this slope is obviously positive. So that's why the derivative is in terms of two variables, both x and y. So I need both the x coordinate and the y coordinate if I'm to find the specific slope of the tangent line at that very specific coordinate point. So sometimes we will be given both the x and the y coordinate point. If we're only given the x value, we would need to then substitute that x value back into the original equation to solve for the corresponding y value, so that we can have both an x and a y to substitute in. And there's probably other information that would be given, but that's just to explain how now our answers are going to have both an x and a y variable when we are using implicit differentiation. Alright, let's move on to another example where I'm going to mix it up with the variables. We're being asked to find dy dt given y to the fourth minus y equals t cubed plus t. So here this is an implicit relation, so I have these two y variables here, and there's no way that I can go ahead and isolate and get the y by itself so that y is a function of the independent variable t. So I'm going to have to use implicit differentiation. And to start this process, I'm going to need to find d dt of both sides. So let's think about what this is asking me to do. Find the derivative of y with respect to the variable t. So I'm going to take the derivative with respect to the variable t on both sides. So d dt of y to the fourth minus y, and then d dt of t cubed plus t. So I'm going to start by taking the derivative on the right side, because on the right side the derivative is being taken with respect to the variable t, and on the right I have all t's. So this is going to be just the very straightforward derivatives that we're used to when the variables match. Well, here I would just use the power rule, so I'd get 3t squared plus 1. No, nothing new about what we're doing on the right-hand side. On the left-hand side, I'm taking the derivative with respect to t of y to the fourth minus y. So here the variables do not match. I'm taking the derivative with respect to t of y. So what we do is we take the derivative as we sort of normally would, and I kind of say that in quotes. So if I were to take the derivative of y to the fourth as if this were the derivative with respect to y, well, that would become 4y cubed. So in other words, I'm using the power rule on this piece, but it wasn't with respect to y, it was with respect to t. So what we're going to have to do is include a dy dt. So what we're really doing is we're using the chain rule. We have this function y that's on the inside, and then we have the outside function, which is the y to the fourth portion, and the derivative of y to the fourth is 4y cubed, and then the derivative of the inside, the derivative of y, is dy dt. So the derivative of the inside y with respect to t is just y prime of t, which we write as dy dt. So now we're done with the first part. Now we take the derivative of the second part with respect to t. So now the derivative of just y, well, again, if this were the derivative with respect to y of y, it would just be a -1. So it would just be that -1 piece. So again, think of like the derivative with respect to x of x. It's just that coefficient in front. It's just the 1. So in this case, -1. But since the variables don't match, the chain rule is taking the derivative of y with respect to t, so we put dy dt. So now we've taken the derivative of both sides with respect to t, and I'm being asked to find dy dt. And there's actually two dy dt's in this problem. So what I have to do is, well, they're already on the same side of the equal sign, so what I'm going to do is factor out the dy dt from both pieces. I'm sorry, dy dt, I need to be careful with that. Dy dt from both pieces on the left-hand side. So dy dt times the quantity, well, 4y cubed is left from the first term, -1 is left from the second term, and all of that equals the 3t squared plus 1 on the right. So if I want to find dy dt by itself, well, this is multiplication, so I'm going to have to divide by 4y cubed minus 1 on both sides. And so these will cancel, so dy dt, what I was in search of in the first place, is 3t squared plus 1 all over 4y cubed minus 1. So this here is going to be my final answer for dy dt. Alright, now let's find dy dx given y to the fourth minus x times y equals x cubed minus x plus 2. So this is an implicit relation because I cannot isolate and get the y by itself here. So I need to take ddx of both sides because I want to find dy dx. So I need to find the derivative with respect to x of both sides. So ddx of y to the fourth minus x times y, and ddx of x cubed minus x plus 2. Alright, so the derivative of the right-hand side is going to be very straightforward. Taking the derivative with respect to x, and I have only x cubed and an x over here. So it's the left side that's going to be tricky. So the derivative with respect to x of y to the fourth. So since the variables don't match here, I'm going to need to use basically the chain rule. So the derivative of y to the fourth using the power rule is 4y cubed. And then the derivative of the inside, the derivative of y, is dy dx. So that's finding the derivative of y to the fourth with respect to x. Now this second piece is new to us so far in implicit differentiation. What we're going to have to do is use the product rule because x is one function of x and y is another function of x. So remember, think about y as f of x. So this is a specific function x times a generic function some f of x. So I would have to use the product rule. So here we're going to have minus the first function, so what I'm going to do is I'm going to go ahead and include parentheses. So I'm leaving the minus on the outside, and I'm going to perform the power rule on just x and y. So x is one function and y is another function. So the first function is x times the derivative of y. So the derivative of y is dy dx. So remember that it's just 1, right? The derivative of y would be 1, but since the variables don't match, I have to include dy dx. So that's first times the derivative of the second plus the second function y. Now here's where a lot of people get confused. All we're doing is putting the second function down. We are not taking its derivative, so we don't need a dy dx just because we've repeated a y. So first times the derivative of the second plus the second function y times the derivative of x. Now, the derivative of x is just 1, and there's no need to include a dy dx because it matched the variable we were taking the derivative with respect to. So this is just plus y times 1. And then equals, so we finished the product rule here, and now the derivative on the right hand side was the nice one, where we can just take the derivative as we normally would, 3x squared minus 1. Now some of these implicit problems can get pretty long, so we really want to stay organized with our work. In this next step, we're going to go ahead and leave the 4y cubed dy dx, and we need to distribute the negative to both pieces here that were from the product rule. So we're going to have negative x dy dx, and then the negative will distribute to the y times 1, so just minus y equals 3x squared minus 1. And now we are trying to find dy dx, so in order to isolate dy dx, I'm going to need to get all the terms with dy dx on one side of the equation, and then all the terms without dy dx to the other side. So I'm going to need to add this y to the other side. So we have 4y cubed dy dx minus x dy dx, and then equals 3x squared minus 1 plus y. Once all terms with dy dx are on one side, I can factor out the dy dx that I'm solving for. And if I do, I will have a 4y cubed left from the first term and a minus x left from the second term. And that whole thing equals 3x squared minus 1 plus y. So the final step is going to be to divide both sides by 4y cubed minus x, so that I have dy dx by itself. So this whole term will cancel with this whole term, and this here will be my final answer. So 3x squared minus 1 plus y over 4y cubed minus x. Now, here's what I'm going to do right now is I'm going to write the answer in a different way and then talk about why I did that. Sometimes this is a multiple choice question and students get this as their answer, 3x squared minus 1 plus y over 4y cubed minus x, and then they look to the answer choices and they don't see their exact answer, they see this one here. So I want to talk about what's really happening between these two answers. Sometimes what the answer key will do is factor out a negative from either the numerator or the denominator and then move it to the opposite side of the fraction bar. So here, basically what I did was I thought about on the bottom factoring out negative 1 and then rearranging these terms. So I have negative and then x minus 4y cubed. So it's like I switched the order of these so that it'd be negative x plus 4y cubed, but then I took out a negative. So think about if I distribute this negative back in, I'm going to get negative x plus 4y cubed, which is what is on the denominator, in the denominator here. And then on the top, if I rewrote this as negative 1 and then plus 3x squared plus y, so all I've done is rearrange things. I put the negative 1 first, then the 3x squared, then the plus y, so that I can think about if I take this negative 1 and multiply it to the entire numerator instead, if I multiply by this numerator, this becomes a positive, and then the negative 1 here distributes to every term, and that's where the 1 minus 3x squared minus y part comes from, and on the bottom, the x minus 4y cubed. So why do they do that? I don't know. It depends on the order in which you sort of started the problem. Maybe you would have rearranged the terms at the start, and then you would have got this as your final answer in the first place. And that may happen. You may get the problem all right and perfect, and it matches one of your answers to begin with, but you may need to do some rearranging with a negative in order to get your answer to match on a multiple choice question. So I just wanted to bring that up. This is a good example to sort of talk about it. As soon as you go, oh, I did all that work and I was wrong, take an extra minute to think about what would happen if you relocated a negative. So this or this is my final answer. Alright, now I want to find dy dx at the value 3, 0, given 2y plus 3 equals x plus sine y. So here, I definitely cannot isolate the variable y, so I need to do implicit differentiation, take the derivative with respect to the variable x on both sides. So d dx of 2y plus 3 and d dx of x plus sine y. And we're going to have an extra piece here. Once we find the derivative, we're going to set the x value to 3 and the y value to 0 to get out a numerical answer for dy dx. So we're finding the slope of a tangent line at a particular point now. So let's go ahead and find the derivative of the left-hand side. Since I'm taking the derivative with respect to x of 2y, the derivative of 2y would just be 2. And because the variables didn't match, I have to include a dy dx. And now the derivative of a constant 3 is 0. So we're done with the derivative on the left-hand side. And then this is going to equal, well, the derivative with respect to x of x is 1. Since the variables matched, I don't need to include anything else. And then the derivative of sine y, well, the derivative of sine y would be cosine y. And then I need to include a dy dx because, again, the variables didn't match. So I need to include dy dx. And one of the biggest mistakes that happens here is that people forget to put the y. So they'll put cosine dy dx, which doesn't make sense. I need to have cosine of a variable. So cosine y dy dx. Alright, so now I need to solve for dy dx. So what I'm going to need to do is isolate dy dx on one side of the equal sign. So I have 2 dy dx already on the left-hand side. So I'm going to go ahead and subtract cosine y dy dx from both sides. And then on the right side, I'm going to have just the 1 left over if I subtracted and moved the other part over. Now that I have dy dx is on the same side, I can factor it out. And then I have 2 minus cosine y as what is left over, and all that equals 1. So now I would just divide both sides by 2 minus cosine y to find my dy dx is 1 over 2, minus cosine y. Alright, so this is the derivative at any point. This is the slope of the tangent line at any value. I specifically wanted the slope of the tangent line at 3, 0. So notice that our answer is only dependent upon the variable y, so all I need to do is substitute in the y value, which is 0, into the cosine function. So dy dx at 3, 0 is 1 over 2 minus cosine 0. Cosine of 0 is 1, so this is 1 over 2 minus 1, so my answer is just 1. Now, one of the reasons I wanted to go over this type of problem is because we didn't actually need to go past this line right here, actually. If we're trying to find a numerical derivative using implicit differentiation, once you've taken the derivative of both sides with respect to x, at this point it may be easier to substitute in the value of x and y into all of the x's and y's that are left over. So in other words, at this step here, 2 dy dx, well, remember, we're trying to find dy dx. So 2 dy dx equals 1 plus, now cosine y, if I substitute in 0, I'm going to get cosine of 0 times dy dx. And now cosine of 0 is 1. So in other words, I have 2 dy dx equals 1 plus dy dx. So now if I subtract the dy dx to the other side, so I have 2 dy dx minus dy dx equals 1. And then I can combine the like terms here. Either you can think about it as either factoring out a dy dx, or this is like 2 dy dx and 1 dy dx, so just combines together to become dy dx equals 1. So that was substituting in the values first, and if you found this to be easier, then that is an option, or if you want to go through and find the general derivative before substituting in the values, that's fine. Often it will be easier to deal with numbers than to do a lot of this algebra, but it's entirely up to you. You get the same answer. So my value for dy dx at 3, 0 is 1. Alright, and this is the trickiest type of implicit differentiation that we will do. So find dy dx given sine of x times y plus x squared equals 3x minus 2y squared. So definitely implicit differentiation. There's no way I'm getting just this y by itself here. So let's start by taking the derivative with respect to x of both sides. So d dx of 3x minus 2y squared. So what makes this one really tricky is this piece right here. The derivative with respect to x of sine of x times y. So I'm going to say that again. Sine of, so chain rule, x times y, product rule. So there is a product rule inside the chain rule here. So the derivative of sine is cosine. And then remember with the chain rule, we leave the inside the same. So the derivative of sine is cosine, and then we leave xy alone. And then we have to multiply by the derivative of the inside, which is a product rule. So the derivative of the inside is the first function x times the derivative of the second. So the derivative of y is dy dx. Plus the second function y, and remember, it's just the second function, we don't do anything to it, times the derivative of the first, the derivative of x is just 1. Alright, and now we can move on to, the derivative of x squared, which is 2x. So sine of xy was this entire derivative here, and then the x squared part became 2x once I evaluated the derivative with respect to x of the left side. And the right side, the derivative of 3x, well, that's just 3. And the derivative of 2y squared, so I'm going to subtract 4y, because apply the power rule. But since the variables didn't match, I'm going to have a dy dx over here on the right side of the equation. Alright, so now, here's where it gets interesting. I'm going to try to use color to indicate what we're doing and why we're doing it. So cosine xy is one whole thing on the outside of a sum. So I have x dy dx plus y. So this whole thing, one thing on the outside, is going to have to distribute to both pieces that are being added together. So I'm distributing here. Imagine if I had just 3 times x plus y. I would distribute into 3. But it just looks a lot messier because it's cosine of xy that's being distributed in. Alright, so now if I distribute cosine xy times x dy dx, here's what it's going to become. X cosine of xy dy dx. And now, for the 100th time, I'm going to remind you that the x does not multiply or go into the cosine function. We can never, ever, ever, ever put something into a trig function or ever take something out of a trig function. So this x on the outside is just being multiplied, and we typically put it in the front. So x cosine xy dy dx plus, for the same reason, this y is just going to go in front of cosine xy. So plus y cosine xy. Cannot put the y inside, cannot take the y out. And then plus 2x equals 3 minus 4y dy dx. Alright, once we've gone to this phase, it's not too bad. So we need to get all the stuff with dy dx on one side. So I'm going to go ahead and add the 4y dy dx. So I'm going to leave x cosine xy dy dx. I'm going to leave that whole thing. And I'm going to add 4y dy dx. So all the dy dx's are on the left. On the right, I have the 3 already. Right, so on the right side I have this 3, and then I'm going to have to move over the y cosine xy part and the 2x part. So I'm going to have to subtract 2x and subtract y cosine xy that was on the left. So that means, let me just try to use a little more color, this part was on the left already, and this part moved to the left through addition. So once I have that set up, now on the left I factor out my dy dx. What's left over is x cosine of xy plus 4y. And on the right, that whole thing is left, 3 minus 2x minus y cosine xy. So to get dy dx by itself, we divide the whole entire thing by x cosine xy plus 4y. And then that big, long, ugly thing is your answer, x cosine xy plus 4y in the denominator. So this cancels, and this is my final answer, which again may vary by a negative if we chose to pull out a negative and put it on the bottom, which on this one wouldn't be likely. This would probably be the final answer, but you still, in all circumstances, should check. If it is multiple choice and your answer doesn't match, you should check the negative part before you go back and try to find maybe where you made a mistake in the differentiation. Alright, last problem. Find the second derivative of y with respect to x given 3y squared minus x equals x squared minus y. So we're asked to find the second derivative here, and we go about finding the first derivative, dy dx, in the same way we've been doing it in these last few problems. So we're going to have to take d dx of both sides. So d dx of 3y squared minus x and d dx of x squared minus y. So the derivative of 3y squared is going to be 6y. It's just the regular derivative, but because the variables don't match, we include our dy dx. The derivative of x is going to be negative 1. And now moving on to the right side, the derivative of x squared will be 2x. And the derivative of y, we're subtracting the derivative of y, which is just 1, dy dx, or just dy dx. Alright, so now what I'm going to do is get dy dx by itself. So I have 6y dy dx on the left. So I'm going to add dy dx to both sides. And then I have a 2x on the right, so I'm going to add the 1 to the other side. And now on the left, I'm going to factor out my dy dx. And I have a 6y plus 1, and then equals 2x plus 1. And then finally, I'm going to divide both sides by 6y plus 1. So I'm going to have 2x plus 1 over 6y plus 1. Alright, that was the first derivative. We were interested in finding the second derivative, so we're going to have to take the derivative one more time. So what that's going to look like is we're taking the derivative with respect to x of the left side, so dy dx, and we're taking the derivative with respect to x of the right side, 2x plus 1 over 6y plus 1. So on the left, and we saw this when we learned our introduction to notation for higher derivatives, this left side is the second derivative of y with respect to x. It becomes exactly what we're searching for. So now we have to think about what's going on the right. Well, hopefully it looks to you like we need the quotient rule, because we do. So we're going to go ahead and do low d high. So 6y plus 1 is low. D high, the derivative of the top is 2, minus high d low. So high 2x plus 1, d low. So we're taking the derivative of the bottom, which has a y in it, and the variable is x. So we're going to have 6, the derivative of 6y, but we need to include a dy dx. And then all over the bottom, 6y plus 1 squared. Alright, so now maybe you're thinking, what do I do next? Well, I don't want to leave dy dx in my answer for the second derivative. So what I'm going to do is I'm going to substitute back in what we already know to be dy dx. So dy dx is 2x plus 1 over 6y plus 1. So that's what's going to go in right here. So I have 6y plus 1 times 2, and then minus, I'm going to put the 6 right here in the front. I have 2x plus 1, and then I'm going to switch colors to indicate what's happening is the dy dx is coming from over here again. So we have 2x plus 1 over 6y plus 1. So that is dy dx, and then it's all over 6y plus 1 squared. So now the rest of what I'm about to do is a whole lot of algebra. Whoops. Alright, ignore that little line over there. So I'm going to have 2 times 6y plus 1 minus 6 times 2x plus 1 squared. So 2x plus 1 times 2x plus 1 is 2x plus 1 squared over 6y plus 1. And then this whole thing is over 6y plus 1 squared. Well, if I don't want to have a fraction inside of a fraction, I'm going to need common denominators up here. So let me change colors to show what I'm doing. In the numerator, I need to put a 6y plus 1 in this denominator, which means I need to multiply the top by that. And there's already one there, so I'm just going to make that squared. And then what I'm going to do is combine those like terms on the top, or I'm sorry, those two fractions with common denominators. So I'm going to have 2 times 6y plus 1 squared minus 6 times 2x plus 1 squared all over. Okay, so try to stay with me on this part. The denominator of the fraction in the numerator is 6y plus 1. So when these two fractions come together, their denominator is 6y plus 1. And then there was already a 6y plus 1 squared on the bottom, so there are 3 copies of 6y plus 1 in the denominator. So if we go back and think about it in terms of numbers, what happens, it's like multiplying by the reciprocal, in other words. So this 6y plus 1 squared is like over 1. So what I did was I came up here and I multiplied by 1 over 6y plus 1 squared. And then this whole thing came together to be one fraction, and there was one copy of 6y plus 1 on the bottom of this one fraction that came together. And then there was 2 copies of 6y plus 1 over here when I multiplied by the reciprocal. So that's why it's 6y plus 1 cubed. So that's all I can do. I just want to remind you, these two things do not cancel because of the subtraction right here. So this is the best I can do as far as simplifying goes. So what I want to recap on is this important step right here, is that when you attempt to find the second derivative using implicit differentiation, you cannot leave the dy dx just as part of your answer. You have to go back and you want it in terms of just x and y, so you need to go back and substitute in what you originally found for dy dx into your second derivative so that it's only in terms of x's and y's. And this was heavy on the algebra. Hopefully you were able to follow along, but the part that I really want to stress is that substitution of the derivative into the second derivative.